Assalamualaikum and good morning, guys.
Morning, Doctor.
Morning, Doctor.
Everybody okay? Right. Bismillahirrahmanirrahim. So today we're going to move to the new chapter, which is chapter 3. The title of chapter 3 is the response and stability analysis in frequency domain. So we have another 2 chapters, which is the frequency response analysis and stability, and then the compensator design in frequency domain. So for chapter 3, okay, you can ignore the number 5.1, 5.2, okay. The content is as shown here, which is introduction to the concept of frequency response, introduction to the simple open loop boat plot overall plotting, analyzing boat plot, Nichols chart, and then MATLAB simulation, which will be embedded in the respective examples throughout the slides, okay? This concurrent within the slides. So the concept of frequency response analysis is basically the input signal is not step anymore, is a sinusoidal input, okay, to generate a sinusoidal response of the same frequency. However, 2 important parameters is difference, which is the input amplitude and output amplitude, and the phase angle from the input, which sinusoidal signals can be represented by a complex number, which is called a phasor, which is this one, okay? So this is the amplitude, this is the cos, and then this is the magnitude, and this is the phase, where M1 and Phi1 is known as the amplitude and the phase angle. Thus, the system can also be represented by complex number, so that the product of the input phasor and the system yield the phasor of the output. So this is the continuing slides of the concepts, where you have the input R, okay, which is the sinusoidal signals, will be injected to the open loop system, and then this is the output, okay, which is represented by this. You can see that there is a slightly change between the amplitude, okay, is a little bit smaller, okay, and then the phase difference, okay, is shown in the diagram, where phase difference have a positive and negative, okay. The output sinusoid is found by multiplying the input and the output of the system. I give you an example how to judge the phase of the frequency response, which is negative and positive. Let us go to this iPad to describe you, okay. 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 So you have the signals here. Is a time. Okay, and the input signal, which is the R of t and C of t. Okay, so let's say the input is here. Okay, so this is the input, and the output is represented by the blue line. Okay, So you can see that there is a phase difference, okay, between the input and output signals. Let's say it is the distance is x, and one cycle of input is y. Okay, so in this case, you have to, if you want to measure the phase difference, okay, it is x divided by y multiplied by 180 degrees. Okay, because one cycle is pi, okay, 180 degrees, and then there is a negative and positive. Okay, is negative if input is leading output, okay, and phase negative is positive if output is leading input. Okay, so how to differentiate between the negative and the positive of the phase in the frequency response? Okay, so in this case, is it the phase difference is positive or negative? Ho Zheng Han.
The input is, I think here the input is leading, so should be negative.
Exactly correct. Thank you very much. So we move to the next slide, which is the concepts for the derivations. So you have the input, you have the output as shown here. Okay, O stands for the input, I stands for the, so O stands for the output, I stands for the input, and we find the magnitude. Okay, so magnitude actually is the ratio. Okay, the ratio between the output divided by input. Okay, and then the phase frequency is the phase of the output minus the phase of the input. So the combination of the magnitude and phase frequency response, we call it as a frequency response, okay, which is represented by this formulation, which is magnitude in terms of phase in degree. So the frequency response of a system with the transfer function is given by this representation, where G, J omega is equal to GS when we replace S is equal to J omega. So in terms of that, so after we get the value of each transfer function, so we have to plot. Okay, so in order to plot for a given transfer function, which is GS 1 over S plus 2, okay, so replace S with the J omega. Okay, so the magnitude of J omega is equal to 1 over square root omega square plus 4. Okay, and then the phase is equal to minus arctangent omega divided by 2. Okay, so after you insert all the value, also the frequency for the magnitude and for the phase, so you will get a lot of data. Okay, a lot of data of the magnitude in and the phase, and then you can plot the frequency response. So you have one way to plot the frequency response is using a separate magnitude and phase plot. Okay, so we are using a magnitude curve, which is a decibel versus log. Okay, so it's a log scale. Okay, the x-axis is the log scale, the y-axis is the decibel, which is 20 log of the magnitude. So the phase curve is the phase versus log omega, meaning that the frequency is under log scale as well. So this is the samples of the separate plots between the magnitude and the phase versus log frequency. So you can see that this is the log frequency, 0.1, 1, okay, 10, and 100. So each of the, here we call it as a decade. This is one decade, okay, first decade, second decade, okay, and this is the third decade, okay. So each decade consists of 10 parts, which is 0.2, okay, 0.3, 0.4, 5, 6, 7, 8, 0.9, then 1.0. Then this one will be 2, this one will be 3, 4, 5, 6 until 10. Then after this one, not 11, but is a 20. It's not 11, okay? It's 20, 30, 40, 50 until 100, okay? So similar to the plot phase as well, okay? But the difference is in phase in degrees, okay? And this one is in decibel, which is 20 log magnitude. This plot is referred to the sample just now, which is 1 over s plus 2, okay? The transfer function of 1 over s plus 2. So here you can see that at 2 radian per second, okay, there is a break frequency over here when the curve is changing from -6 decibels and it goes down, okay, with the slope, okay. There is a slope line here, okay. Okay, so the slope is -20 decibel per decade. And here too also have a break frequency, which is over here is 45, -45 degrees. Okay. So another way beside boat plot is to use a Nichols chart. Okay, so Nichols chart is one of the alternative when you have a frequency response data of magnitude and phase, so you can plot the frequency response via this chart. Okay, so the unique of this chart is the open loop and the closed loop data you can see in one display. Okay, which is here. So this part you can see that there is a magnitude outside the chart. Okay, this also degrees. This one outside the chart, we call it as open loop magnitude. Okay, this one is open loop phase. Okay, but inside it there is also meaning that the phase and the magnitude and the phase. Okay, which is here. So this is 1.1, 1.2, 1.4 decibel. So this one is known as the closed loop magnitude. Okay, closed loop magnitude. And also the blue line is the closed loop phase. So the log magnitude and phase frequency response curve as a function of log, we call it as a boat plot. Okay. Boat plot is technique for analyze and design of a control system by considering these transfer functions. Okay, GS is the open loop transfer function where K is the gain, Z1, Z2, and so on is the zeros, and P1, P2 is the poles, and this will indicate the type of the system. Okay, the type of the system. So if m is equal to 0, meaning that the system is type 0. If m is equal to 1, it is type 1. M equal to 2 is type 2, and so on. Then after we get this transfer function, so we have to apply the magnitude formula for each of these poles and zeros by replacing S is equal to J omega. And then after you replace it, you convert it into decibel, which is the 20 log G omega, where from here it will be 20 log K plus 20 log G omega plus Z1 plus another zeros plus another zeros, and then divide will become a negative, which is a negative 20 log the first pole minus 20 log the second pole, and so on. So the phase frequency response is given by this formula, which is Gj omega is equal to degree of constant K plus the degree of the zeros plus the degree of the second zeros minus the degrees of the first pole, second pole, and so on. So if we know the magnitude and the phase response of each term, total frequency response can be obtained by algebraic sum of each term. So this frequency response can be simplified by using the straight line approximations. Okay, so we have two methods in order to plot the both plot. The first one is using the exact calculation, which is meaning that we are using real data. Then we plot. We connect each dot, okay, until we get the graph. The second one is by straight line approximations. So both will do, okay. So therefore, total frequency response can be obtained by graphic additions. What I'm trying to tell you is that there is a two-way if we look at here, okay. So this is the real plot, okay, where the data is represented by the blue line, okay. So let me share with you the plotting. I think using iPad is better. Okay, this one, eh? So the blue one is the real. Eh? So what is the straight line approximations? The straight line approximations is here. Okay, this is the 2. Okay, the break frequency. Okay, and then it will go down straight. Okay, this one we call it as a straight line approximation. Okay, similar to this one as well. Okay, so 0.1, 0.2. Start from here. Okay. So 0.1, this is a 0.2. Okay. And this one is here. Okay. It's 20. So we connect this line. Okay. Okay. So both are right. The blue one and the right, the red one is both can be used. Okay. So if you're using a computer, using a MATLAB, so the plotting will be the blue line, which is the real data. But if you are not using a computer, using a semi-log paper, okay, semi-log paper. It's like a graph, but it's not a graph, it's a logarithmic scale, okay? Okay, so you will get, you have to use the straight line approximations. Okay, guys, can follow?
Yes, doctor.
Yes, doctor.
Some hiccups, but yeah, I can follow so far.
So next we go to the both plot factors. So since our transfer functions have for example, a transfer function like this just now, 1 over s plus 2. Okay, so we have a, let's say we have a constant k, gain. So this one is a gain. So this one is a pulse. All right. So sometimes they have a zeros factor. Sometimes they have a gain factor. Sometimes they have a pulse factor. Sometimes they have a, what do you call that? Integration 1 over s. Sometimes they have a derivative s. Okay. And sometimes they have a second order complex conjugate code. Sometimes they have a complex conjugate zeros. Okay. So a lot of factors. So I list out the factors, which is the constant k, zeros at the origin, pulse at the origin, which is 1 over s. This is gain k, s, 1 over s. Zeros at the real axis, which is s plus a, and 1 over s plus b. So let's see the plot for constant k. K, let's say it's 10. If the k is equal to 10, so 20 log 10 is equal to 20 decibel. Okay. So we see the plot for the magnitude, plot for the phase shown here. Okay. So it is a constant, okay? And the phase is 0 degrees. Okay. The plot kan dia. Okay, omega dB degree. Okay. So 20 decibel. Okay. And phase (0 degrees). Okay, that is for the constant. Then for zeros at the origin, okay, which is S, gs is equal to S. Replace S with the j omega and 20 log omega. So it is 9. The phase will be 90 degrees, and this one will be a straight line with the slope 20 decibel per decade. Okay. So usually we are not using octave. So we are using positive 20 decibel per decade. So how you calculate that? So it's very simple actually. So you get the 0.1, you get 1 over here. So this one is 1 decade, am I right? Okay, and the difference between the here is 20. Okay, 20 dB. So that's why the slope, okay, the slope here is positive 20 dB per decade. Okay, decade to meaning 1 decade. 20 decibel is meaning the difference, the changing, the delta M, the changing of the magnitude from 0.1 radian per second to 1 radian per second, which is 20 decibels. That's why the slope is 20 decibel per decade, positive, because it's like this, the graph is like this, okay? And then the phase will be 90 degrees, a straight line. Then we go to the pulse at the origin, which is 1 over s, is the pure integrations, okay? So it is invert from the derivative. So this is the plot, is a straight line with the slope of minus 20 decibel per decade, okay? Jadi slope-nya adalah itu 3 segi tangent sini. Okay. So the changing is 20. This one is 1 decade. So the slope will be minus 20 dB per decade. Okay. And the phase is inverse from the derivative, which is minus 90 degrees. Okay. So zeros at the real axis. Okay. So for example, 1 over S over A plus 1. Okay. So we have to derive the low frequency, the exact frequency, and the higher frequency. And we will get for low frequency 0 degrees, 45 degrees, and 90 degrees at the low frequency. With the gain formula as shown here, square root omega divided by A square plus 1, and the phase is arctangent omega divided by A. And the plot is shown here. As I told you before, we have the actual or the real, the same thing, real and actual. And this one is the asymptotic approximation. Asymptotic too, meaning that is a straight line approximation. Okay, it's another word. Okay, so please remember, actual is real, okay, and asymptotic approximation is the straight line approximation. So there's not much different. Okay, here, same here, over here, but the change is this part, okay, where this one is known as the break frequency. Break frequency. Okay. And what is the slope of this line? The slope of this line is positive 20 decibel per decade. Okay. Okay, this is the break frequency. Okay, low frequency and high frequency. Simple. And the phase is shown here for the phase. Okay, so since the break frequency at 1 radian per second, so the break frequency occurred at this point, which is 45 degrees. Okay, so you can see that the straight line approximation is here. Okay, the black is real. Okay, so you can see the border, which is 1 decade before break frequency, which is 0.1, and this one is 1 decade after break frequency, which is 10 radian per second. Okay, so the break frequency occurred at 1 radian per second between 0.1 and 10 radian per second, with the phase is 45 degree. Okay, so what is the slope of this line? The slope is positive 45 degrees per decade. Okay, so this is the sketch of the phase for the poles at the zeros at the transfer functions. Okay, so this one is the break frequency, BF, yeah, low frequency asymptote and high frequency asymptote. And this line is known as the asymptotic approximation, meaning that is a straight line approximations. Then poles at the real axis. Just now is the zeros at real axis. Now is the poles at real axis. We assume the transfer function is gs 1 over s divided by a plus 1. Okay, so we replace s with j omega. Then we find the magnitude. Okay, so this is the magnitude, 1 over square root omega divided by a square plus 1. And the phase is minus arctangent omega divided by a. At lower frequency, omega less than a is 0 degrees, and omega is equal to a is minus 45 degrees, which is the break frequency. And at omega, the highest frequency, omega greater than a, which is minus 90 degrees. So you can expect the plot is something like this, okay? So this is a 0 decibels, and after the magnitude, see the break frequency, so we'll go down with the slope of minus 20 decibel per decade. Okay. So low frequency asymptote is 0 decibels, high frequency asymptote with the slope of minus 20 decibel and break frequency at a radian per second. And similar to the for the phase as well. Okay, it is inverse from the zeros at the real axis. So you start at 0 degree, ended at minus 90 degree. And at the middle here is the break frequency, which is the minus 45 degrees. Okay. And the slope is minus 45 degrees per decade. Example 1. Okay. I invite one student to read. Azizun. 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 Tidur. Ali Imran. Ali Imran.
Yes.
Can you read the question? Example 1, please.
Sketch the Bode plots for the open loop system shown where GS equal to K S plus 3 over S plus 1 S plus 2. Use the command in MATLAB to get the actual Bode plot using the command Bode G.
Bukan komen, command.
Command Bode G.
Yang tersasul pula. Right, so how to plot? First, we identify the factor inside here. So K is a gain, kan? S plus 3 is the 0 at real axis. S is the poles at the origin. And S plus 1 and S plus 2, 1 over, okay, is the poles at real axis. Okay, so in exam and test, I would like to remind you that you are not required to plot the Bode plot. Okay? You are not required to plot the root locus, but the root locus are given, and the Bode plot is given. Okay, so you don't have to plot, wasting time. So they give you the plot, and from the plot you have to extract out the information that is relevant to the question asked. So MATLAB code to generate, as usual, you use this command, S is equal to TF apostrophe S apostrophe. Assume K equal to 1. Okay, and then write this command, G is equal to K, S plus 3, S 3, multiply. Then the command is Bode G. Okay, and then you find the grid. Okay, can we go to the MATLAB? You want to look? You want to have a look?
Yes, please, doctor.
Open your MATLAB. So S is equal to transfer functions. Okay, and then so G is equal to 1. Okay, we already assume K is equal to 1, multiplied by the poles at -3, which is S plus 3. Okay, divide by S, the poles at the origin, multiplied by the poles at real axis -1, and then multiplied by poles at the real axis -2. Okay, so this is the questions. Okay, so it's a third order system. Okay, it's a third order system because the denominator is at S cubic, right? Then this is a system type 1. Okay, type 1 because the system have poles at the origin 1 over S. Okay. Then type the command. Is it R locus? No, it's not R locus. It's BODE. BODE. BODE G. Okay. Right. So you can see that on the bottom left is busy. It's calculating. Bottom left there is busy. Okay, it's done now. Okay, and then we put the grid here. Okay, never mind. Okay, here. So I share the screen. Okay, can you see? Can you see? So you use your mouse, right click, okay, put the grid here. There you go. So that is the grid of the log scale. Okay, starting from 10 power of -2, which is 0.001, 0.1, 1, and 10. Okay. What else you can do? You want to make it 5 decade, also can by using the properties. Okay, make it 5 decade. Okay, so instead of 10, we put 100, 1,000. Okay, close. See, so you have a 5 decade boat plot. Okay, this is this is 1 decade. Okay, this is second decade. Okay, third decade, fourth decade, and 5 decade. Okay, decade, D-E-C-A-D-E, decade. Decade meaning 10. 10. Nur Aina Syafika. Nur Aina Syafika.
Yes, doctor.
What is your age now? Umur berapa?
22.
32?
22.
22. So Nur Aina Syafika is 2.2 decade age.
Paham?
2.2 multiplied by 10, 22. Okay, Nur Aina.
Yes.
My age is 5.5 decade. So what is my real age?
55.
55 what?
55 years old.
55 years old. So you must understand. You understand the concept now. Okay, which is shown here. So what else you can get from this plot? Let us explore. Peak response. Ada tunjuk? Tak ada. What else? Minimum stability margins. Ada. Oh, tu ada. Okay. And then the all stability margins. Okay, so shown here is the phase margin. Okay, phase margin. Just give you some teaser because you will see this word phase margin, gain margin. Okay, 36.9 degrees positive. It occurred this phase margin occurred at this point when the magnitude crossed 0 decibel. Okay, this is a 0 decibel. When the magnitude crossed the 0 decibel, the frequency is 1 radian per second. Okay, and at 1 radian per second, the gain margin is 36.9. How do I get 36.9? Okay, how do I get 36.9? That will be discussed in the next lecture. Okay. At this point, you must know how to plot the boat plot using a MATLAB command. Okay. Right. So if you want to do it manually, so you have to plot one by one. So you have to plot the gain, okay, and then what else? S plus 3, S plus 3, then 1 over S, then 1 over S plus 2, okay, and then 1 over S plus 1. So you have to plot, and then like this, you plot, and then at the end, you sum up everything, okay? This is using a manual. You can see there's a lot of unit there, okay? Decibel, minus 20 decibel, minus 40 decibel, and so on. So boat plot for the second order. So second order system is represented by this standard formula, which is the omega n square over s square plus 2 zeta omega ns plus omega n square. So we replace it with s is equal to j omega inside. Then we simplify. So we have at low frequency. Okay, the magnitude is 1, and the phase is, the magnitude is 0 decibel. And the phase is 0 degrees. At high frequency is the magnitude will be the phase is minus 180 degrees. Then we can plot it here, okay, where the break frequency is omega n, okay, and this slope is not minus 20 decibel, but the slope is minus 40 decibel per decade. Okay, how I calculate that is very simple. Take a triangle. Okay, so this is 1 decade, and this one is 40. Am I right? 80 minus 40 is 40. So that's why you get minus 40 decibel per decade. So that is the way we calculate the slope. And the second order for the phase is shown here, where the break frequency occurred at minus 90 degrees. Start from here, 1 decade before, which is 0 degree, and then it goes down to minus 180 degrees at 1 decade after omega n. What is omega n? Tanyalah, saja je tanya. What is omega n? Azira Ahmad. Azira?
Yes.
What is omega n?
Frequency. Wait, I forgot.
Break the purple.
Break frequency.
Break frequency. Okay, which is equal to the undamped natural frequency lah kan? Betul? Betul?
Yes.
Ya. Oh, tanya. Okay, so that is the second order system. Okay. So both plot for the second order, when we normalize, okay, at break frequency, we get minus 90 degrees. Okay. Right. So both plot for the second order, the plot is shown here in the real. This is the real data standard curve. Okay. So the straight line approximation is shown here. This straight line approximation. Okay. But if you use a computer and you vary the zeta, vary the zeta. What is zeta? Nurliana Izzati. What is zeta?
Yes, Doctor.
What is zeta?
Zeta. Betul.
What is zeta?
Tak ingat lah. Damping ratio.
Damping ratio. Ingat. Mana belajar tu chapter 2 banyak ni saya cakap zeta line cross root locus. Okay. So when you vary the zeta from 0.1 to 1.5, okay, so you will get a several plot for second order magnitude frequency response. Okay, so each of them will give you a different peak amplitude. Okay, at the omega n. Okay, at the omega n break frequency. And same to the phase as well. When you plot the phase in the real time computer, so you will get different plotting for each zeta. Okay, so 0.1, 0.2, 0.3, 0.7 is considered what category of second order? 0.1, 0.2, 0.3, 0.7. Asim Jamil.
Yes, Doctor.
0.1, 0.2, 0.3 until 0.7 is second order what category?
I don't know, Doctor, actually.
I don't know. Astaghfirullah al-azim. Okay. So we ask another
Is it
student.
under damped, Doctor?
Who is that?
Tekpal.
Huh?
Tekpal, Doctor.
Telpel. Oh, Telpel. Under them, Under them. Okay. 1.0. Alisha Zaidi. 1.0. Second order what category? Alisha Zaidi. Tak datang? Jawab.
And then
And then? Astaghfirullahaladzim.
tickling them.
Budak-budak ni. Apa benda dia belajar pun kita tak tahulah. Tickle them. And the last one. Iskandar Zulkarnain. 1.5 is second order category what? What category? Iskandar Zulkarnain. Tak datang? Datang ada ya, dia tak datang. Okay. Tak datang kira tak datang. Bagi Nik Umar lah. Nik. Sila jawab Nik. 1.5 second order what category?
It would be overdamped.
Okay. So second order system category. Number 1, zeta is equal to 0, and then Number 2, zeta is equal to 1, critical. Number 3, zeta greater than 1 over. Number 4, zeta is between 0 and 1, under them. And number 5, zeta is less than 0. This is what? Category of what? Zeta
Negative damping.
Huh?
Negative damping.
Negative damping. Remember lah. Lupa-lupa ni, aduh, dah berkarat lah. Baru 22 tahun, dah berkarat. Okay guys, we have a rest for 10 minutes, okay? Boleh? 10 minutes rest. Don't go anywhere, stay tuned.
living, taking some time from each other. Sometimes distance can bring two people back together. I went away, but all I did was missing you. I was selfish, but I came back to tell you. I pray every night for someone to mend my broken heart. When you couldn't see the light, you walking with me in the dark. And all this time, you were right there from the start. All I asked from you was just to stay where you are. I've been fighting all my demons away so that I could become the best thing you had. The only person who understands me is you. The only life I ever wanted is with you. I pray every night for someone to mend my broken heart. When you couldn't see the light, you walking with me in the dark. And all this time, you were right there from the start. All I asked from you was just to stay where you are. I pray every night for someone to mend my broken heart. When you couldn't see the light, you walking with me in the dark. And all this time, you were with me from the start. All I asked from you was just to stay where you are.
Okay, guys, we continue with example 2. Can you hear me?
Yes, doctor.
Okay. So the example 2 is another examples. Sketch the workload for the GS for the unity feedback system. Okay, unity feedback, where the open loop transfer functions is represented by GS. R is the input and C is the output. And of course, E is the error, R minus C. Okay. So using MATLAB, so we're going to plot it. Okay. Actual plot, eh? Okay, go to the.
Sir, we cannot see the screen.
Oh, I'm sorry. Okay. Okay. Example 2. Ahi. Example 2. S plus 3 over S plus 2, S squared plus 2S plus 25. So we're going to plot using a MATLAB. So the G will be different. Okay, G is S plus 3 divided by S plus 2.
Doctor,
Yep.
are we required to draw the plot diagram in the test?
No. You are
So-
not. You are not required to plot the both plot during the exam and test. The plot will be given.
Okay, so we have to extract the information from it.
Yes. Yeah. Okay. So multiply S squared plus 2 plus 2 multiplied by S plus 25. Okay. So it's a third order system. Okay, in example 2 is a third order system. The type is 0. Okay, there is no poles at the origin. So use the command both G. Okay, then I share the figure. Okay, so there you go. So since our transfer function have a second order complex conjugate poles, S squared plus 2S plus 25. So the plot is shown here. Okay, so just display the grid. Okay, and try to make it 5 acre. Okay, 10,000. See? Okay. So you can see here the characteristics of this boat plot by looking at the peak response. There you go. That is the peak response. The value is minus 19.1. Okay, at 4.8 radian per second. So 4.8 radian per second is the break frequency. Okay, is the break frequency, or I can say not the break frequency, is a peak frequency. I'm sorry, peak frequency at the peak gain, minus 19.1 decibel. Then the minimum stability margins, it's not available. And all stability margins, also not available. Okay. Okay, then the solution is here. So we have a second order systems, yeah, where the omega n is equal to 25 and zeta is equal to 2. How do I get this calculation? How do I get this value? Azira Ahmad.
Okay.
How do I get this value? 5 and 0.2.
Characteristic equation.
Characteristic equation. Characteristic
Equal
equation.
to 0.
Okay. No idea. Alisha Zaidi. How do I get 5 radian per second and zeta 0.2? Not from the plot, from the transfer function. Alisha Zaidi.
Using formula comparison between formula second order.
Do you mean like this?
Yes.
Okay, so you compare. Okay. Okay. Do zeta omega. Okay, okay, guys, clear?
Yes.
Then you normalize. If you want to plot manually, okay. So you plot manually each factor, and then you sum all the factors. Okay, just to inform you how we do it manually. But in the exam, you don't have to do it manually. All plots are given. Okay. So this is the coding that I use for the plotting just now. Okay. For these particular transfer functions. Okay. Stability. Okay. So stability is the important issues now. Okay, where unstable system is very harmful, dangerous to human. Okay, and so you have to make sure our system is stable. The symptom of the system become unstable when the signal give a critical response. Okay, so recently we have a case in Indonesia. You know about it? Is what do you call this?
The submarine.
Submarine. The submarine. Okay. So the submarine, when launched from the port, from the Air Force port, is stable, but when is in the sea, it become unstable. So it goes down about 1 kilometer deep with high pressure. High pressure. So this one is made in Germany. Okay, very old submarine. Then they upgrade. Upgrade meaning they change all the parts, okay, and everything. So I suspect during the upgrading, maybe there is not according to the standard. So the submarine is out of order, from stable, become critical, and become unstable. So when it's unstable, so it affects everything, all the system, especially the oxygen tank, because this submarine will go down deep, about 500 meters down to the sea. So with the high pressure, so it will explode the oxygen tank if the system is unstable and all are died. Okay, so saya sedekahkan Fatihah kepada semua.
Very terrifying. That's
very
terrifying.
Yeah, there is no because there is no equipment that can go inside 1 kilometer deep at the Bali seashore in Indonesia. So what has been reported officially, all crews of the submarines are dying during the Ramadan. Okay, so this is sample of the unstable system. So therefore, stability of closed loop system can be determined using an open loop system. Okay, open loop. Please remember. Okay, you want to find stability of both plot must be in open loop system. A closed loop system is stable if the magnitude of the open loop system is less than 0 dB at the frequency where the phase is plus minus 180 degrees. So sketch the both plot and here to get the actual plotting. Determine the range of K within which this is example 3, okay? First, sketch the both plot, use MATLAB to get the actual plotting, determine the range of gain K. K is gain, which the unity feedback system is stable, okay? So let G is equal to S plus 2, S plus 4, S plus 5. For convenient, choose K is equal to 40. Assume it. Okay. So we plot it using MATLAB. So G is equal to 40. Okay, divide by S plus 2. Okay. So we have 3 poles, okay, -2, -4, and -5 at the real axis. Gain at 40, no zeros, no second order poles, and no second order zeros. Okay, so we plot both G. Okay, so we already get the plot here. Can you see?
Yes, yes, we can see.
For the grid. Okay. Okay, and then find the range of gain K. Okay, you already plot. So we go to the right click of the mouse and minimum stability margins. Okay. Okay. So this is the maximum amplitude, which is 0 decibel, 0 decibels. Maximum phase. Okay. Phase. And then this one is not important. So the important thing is this one. This one. Okay. The gain margin. Okay. So gain margin is 19.5 positive. Okay. 19 positive 19.5 decibel. Okay. So the frequency is 6.16 radian per second. Where it occurs at here when the phase cross minus 180. Okay, so we scan at the phase here. Okay. Okay. We scan the frequency 6.16. So at frequency 6.16, the phase degree is minus 180. So this gain margin occurred at frequency 6.16 decibels. Okay, so it gives you positive 19.5 decibel. How do I get the gain margin? Gain margin is here. Gain margin is equal to 0 minus 19.5. Okay, because at this point the value of the magnitude is minus 19.5 decibel. So gain margin formula is 0 minus 19.4, so it's a positive 19.4 decibel. Okay, the margin. Yeah. This one is called as a gain margin. Okay, it occurred at 6.16 radian per second, which is here, where the phase cross at minus 180 degrees. Okay, that is the gain margin. Any question?
Yes, doctor.
Yeah.
How do we get the range of gain from that plot?
There's a way on it. Okay. So here is the solutions. When k is equal to 40, at phase minus 180 degrees, omega n, omega gm, omega gain margin, 7 radian per second. From the computer, 6.16 radian per second. Okay, so more or less the same, 7 and 6.16. Magnitude is minus 20 decibels, so therefore the gain margin is 0 minus 20, which is 20 decibel. The one that we get is positive 19.5 kan. So dia lari sikit. There is a more or less reading. Okay, I think by 20 decibel is by straight line approximation. 19.5 is based on the actual or real computing. So the system stable at k is equal to 40. Okay, therefore, an increase in gain of 20 decibels is possible for stability before the system become unstable. Hence, the gain for stability is 400, which is 40 multiplied by 10. So the range of stability is become 0 to k 400. So we change the plot. Okay, we change the plot, we increase the gain. Instead of 40, okay, just now, okay, so we change to here. Okay, we change to 400. Okay, and see the plotting. So this is the plot when we change from 40 to 400. Can you see? Okay, and then we find the stability margins. Right? So what is the value? So now the gain margin is minus 0.49. Previously positive 19.5 decibel. If the gain margin is positive, meaning that the system is stable. If the gain margin is become negative, it is meaning that the system is unstable. Okay, so now the gain margin is negative. Okay, so where this 0.491 come from? It come from here, just above the zero. Okay, 0.491 decibel positive. So the gain margin now is 0 minus 0.491. So that's why you get a negative 0.491 decibels. Okay. So the system is unstable. Because of the negative. Okay. And this one is the point here. Okay. And the phase margin also negative. You can see that the phase margin is negative and the gain margin is positive, negative. Okay. So when both gain margin and phase margin negative, so it shows that the system is unstable. So how do I get phase margin? Phase margin occurred at frequency 6.32. Okay, 6.32 is here. It's very near. 6.32. Dekat-dekat. Okay. Okay, when the magnitude is crossed at 0 decibels. Okay, so phase margin when magnitude cross 0 decibel. Okay. Or you can simply using a round twist if you want to see the exact value of the apa nama ni, the critical gain. Okay, we can calculate using a round twist. Okay, what is the transfer functions just now? Yeah, here you go. Okay, k s plus 2, s plus 4, s plus 5. Okay, let's go calculate using a round twist. S plus 2, s plus 4, s plus 5. Okay, so we assume k is equal to 1. Okay, so gs become 1 over s plus 2, s squared plus 9s plus 20. 1 over 2 s cubic plus 9s squared plus 20s plus 2s squared plus 18s plus 40. 1 over s cubic plus 11s squared plus 38s plus 40. Okay. So next page. Sorry. So the closed loop transfer functions. One over, sorry, ds, 1 plus ds. Okay. So ds will become 1 s cubic plus 11s squared plus 38s plus 40 plus 1. Okay. 40 plus 1. So this one will become 41. Okay. And the characteristic equation is s cubic plus 11 s squared plus 38s plus 41 equal to 0. Okay. And these values insert into Ruth-Lewis table. Remember, Ruth-Lewis table. Temple. Do you remember? Temple's not here. Nuliana, Izati. Remember Ruth-Lewis table?
Yes, doctor.
What is it?
S cube. 1.
1, 11.
11. 38.
This one not K lah. We assume, tadi kita assume 1 kan. Sebab kita nak tahu range of K. So we just put K here. So instead of 41 plus 1 ni. 40 plus K. Okay.
40 plus K.
40 plus K sebab kita nak tahu range of K kan. 40 plus K. Okay. 38S. 38 kan? 38. Then 40 plus K. Okay, do you remember here how to calculate this? Ni,
Yes.
Yes.
ingat, ni. You can get the range of K from the graph by try and error. By try K is equal to 40, 100, 400, okay, until you get negative. Or you can calculate using a manual, which is using a rough waste. 38, 40 plus K, okay, divide by 11. Eh? Hello, everybody sleeping. 40 plus K minus 38 minus 11 divided by 11. How much? Kira, kira-kira. 38 darab 11. 418. This one is 418. So you will get
K minus 378.
P plus K minus 418 n. Minus 418 divided by 11. And this one can be 40 minus 418. Okay. Minus 378. 378 plus K divided by 11, which will be here. Okay.
Doctor, should be in positive.
Positive. What positive? Oh yeah, positive. Yeah. Because of this end. So this one will be minus K. Am I right? Minus K. Okay. So I delete this one. So this one will be 378 minus K 11. Correct? Correct? Guys?
Yes, doctor.
Yes, doctor.
Jangan biarkan I keseorangan.
Sorry, doctor.
Right, so okay, so this one 0, and this one, macam mana nak calculate? Pergi bawah tak payah, kan? Tak payah. Ini sampai S1, S plus 1 ke? Ke sampai S plus 0?
Sampai.
Sampai S plus 0?
Ya.
Okay. Kalau sampai S plus 0, yang ini akan menjadi minus 11 lo tambah K 378 tolak K bagi 11 kosong ya. Bagi dengan 378 minus K divided by 11. So you can calculate lah ni. Okay. So let's say we take this one. This one is already positive. This one already positive. So 378 minus K divided by 11 greater than 0, first column. So 378 minus K greater than 0 minus K greater than minus 378. So I'm doing magic. Okay, I blow this equation. So it will become K positive 378. Okay, so this is the range. Okay, so the range will be 0 between K between 378. Okay, the one that we used just now is 400. Am I right? So this is stable, range of stability. K greater than 378, what happened?
Unstable.
Unstable. K is equal 378.
Critically stable.
Oh, critical. Okay, so that will give the answer on Nick Omar question just now. Okay, Nick.
Thank you so much, Doctor.
Okay, so this one dia give 400, tapi 400 just now is negative kan? Actually below it. I think it's about 378. Okay, so you will get critical. So critical ni, let's say we simulate, huh? Nothing harm, isn't it? We want to see what happened, 378. So we share with the MATLAB here. Okay, we change from 400, we change to 378. 378 begin. Okay. Then boot G. Okay. And we find the stability margins. See, what is the value of the gain margin?
Zero. Very close to zero. Very close to zero. 4.5 E
It's
negative
basically
5, so very
zero.
small.
Just say it's zero.
0.000 is a 0 decibel. Can I? 0 decibel, am I right?
Yes.
Yes.
0 decibel. Jangan tertipu dengan nombor tu. Exponent minus 0.5. And the phase margin?
It's also zero.
Also 0. 0 degrees. Gain margin. Ini gain margin. The unique of the system when it's become critical is the omega CG, the omega GM for the gain margin is equal to the omega of phase margin at 6.16 radian per second. Can you see the difference? Okay, so omega gain margin occurred here, omega gain margin, and omega phase margin occurred here, omega phase margin. So this one, I call it as a critical, okay, marginal. It's in between stable and unstable. It's between left half plane and right half plane. So bila dah critical, so it is a signal that the system is not stable anymore and will become unstable and will sink down to the sea 1 kilometer deep. That's why when the system become critical, usually they will install alarm, okay? Alarm to indicate, to remind people that the system is danger, under danger, and will explode and will harmful to the human. Is it okay? Understand? Do you understand what I'm
But I
saying?
thought, Doctor, the critical means it's the most stable it can be. Is that
No.
not?
Critical meaning that the response is swing. The time response is swing. Swing. Constant swing. Then when it become unstable, the time response will be like this. Become bigger towards the infinity. Stable meaning the response go up with overshoot, then go down, then it's stable like that. This is stable. This is good. This one not good. This one also not good. Alert that the system will become unstable very soon. Okay. Then actual results. System will become critical at K is equal to 3.78 and 6.16 radian per second. Okay. where the gain margin 0 decibel, the phase margin 0 degrees, and the gain margin frequency and phase margin frequency is equal at 6.16 radian per second. So this is the, before I go to the gain and phase margin definitions, I already discussed with you from the MATLAB plot that we can get this value of gain margin and phase margin via computer. So gain margin and phase margin are two quantitative measurements to indicate how stable the system is. So system with greater gain and phase margin can withstand the greater changes in the system parameters before it becoming unstable. So the gain margin GM is the change required in open loop gain at 180 degrees phase shift to make the closed loop system unstable. So this one occurred when phase curve cross minus 180 degrees. So the gain margin is found by using the phase plot to find the gain margin frequency or omega GM, where the phase angle is minus 180 degrees, as I said before. At this frequency, look at the magnetic plot to determine the gain margin with the gain required to decrease the magnitude curve to 0 decibels. While the phase margin is the change required in the open loop phase shift to make the closed loop system unstable. So the phase margin is found by using the magnitude curve, okay, at omega phi m, where the gain is 0 decibels. So this one, when the magnitude curve cross 0 dB line. Okay, so it will be give you the omega PM or omega PM, same thing. So I usually call omega PM and omega GM. PM stands for phase margin, GM stands for gain margin. Okay, so it's shown here. Okay, you can see that when the phase plot cross minus 180 here, minus 180 degrees. Okay, so it will give you omega GM and it will give you the gain margin over here. But when the phase margin, when the gain cross 0 decibel here, so it will give you omega PM, omega PM, which is give you the gain phase margin at that particular point. Can you remember this? Remember. Huh? Very important, omega M and GM. Okay, so Azira Ahmad. Azira,
Yes, Doctor.
can you read the question for me?
Consider a unity feedback system GS equal to 200 over S plus 2, S plus 4, S plus 5. Using MATLAB, find the gain margin and the phase margin for the board plot.
Okay, so we're going to plot it here. G is equal to 200 over S plus 2 multiply S plus 4 multiply S plus 5. Okay, both G. Okay. Can you see the plot?
Yes.
Okay. find the characteristics. There you go. There is your gain margin and your phase margin. This one is gain margin. Okay. Okay. Positive 5.53. And this one is your phase margin, 23.5 degree positive. Raja Ahmad. Raja Ahmad.
Ya, Doktor.
What is the value of omega GM? Gain margin
5.53.
Alah. 5.3 tu gain margin.
Oh, Doktor.
Okay. Puasa ke? Puasa kan? Lalu ke? What is the value of the frequency of gain margin? Omega GM. Tak tahu. Nurliana?
4.51.
Taklah. Abdul Rahman. Abdul Rahman, what is the value of the omega gain margin frequency? Tak tahu. Telpelgil? Telpelgil, where are you?
His phone is connected. Can I answer on his behalf? He has a problem with internet.
So what is the value?
6.02 sorry, 6.16 radian per second.
6.16, yeah. 6.16. Raja. 6.16 radian per second, Raja.
Okey, Doktor.
Kodok balik. Omega phase margin berapa? Phase margin 23.5 degree, 23.5 degree. What is the frequency of phase margin? Raja.
Oh, ya, Doktor.
Gain phase margin frequency.
6.61.
Mana kau tengok? Alah tu. Tengok kat phase margin. Ni lah, nampak? 23.5. Apa frekuensi dia?
4.51.
4.51 radian per second. System stabil or not stable, Raja? Stable or not stable?
Critical stable.
Alah, stable. Why? Due to gain margin, phase margin, positif. Cuba sebut. Cuba sebut, Raja. Tak ada lain.
So if one of them is negative, will it still be stable?
No, it should not be like that.
Oh, cannot. So if one negative, both are negative.
Ada. No such thing. So the gain margin, phase margin positive, or gain margin, phase margin negative, or gain margin 0 decibel, phase margin 0 degrees. That is critical. Positive, stable, negative, unstable, 0 dB and 0 degree is critical. Catch it?
Yes, thank you, Doctor. Doctor, the solution is off from our result.
Yeah, compared to the notes is quite different, but it's okay. Okay, acceptable, because this one is a straight line approximation using a manual drawing. The one that I show is actual, so they're a little bit the value a little bit not the same, but acceptable. Okay.
Okay.
Right. I think we stop here. Example 4. Okay. Example 4. Then we will continue on Wednesday, inshallah. Any question?
No.
Senyap je. Puasa-puasa semua senyap. Akhi, Arab brothers, any question? Arab brothers? Ahmad Abulita,
Thank you, sir.
understood? Anta fahimta?
Yes, fahmt.
Okay, so inshallah you see you on Wednesday. Subhanallahi wa bihamdihi, subhanallahi wa bihamdika. Asyhadu an la ilaha illa anta, astaghfiruka wa atubu ilaik. Thank you very much. See you next Wednesday.
Okay, Doctor.
Thank you, Doctor.
Assalamualaikum.
Thank you, Doctor. Assalamualaikum.
Next Tuesday.